Hello there.
With the ground beneath your feet, with a whisper in the trees. Do you feel us watching?
Good evening and welcome everybody, it's Obi-Wan Pez4 and Simplex Pachinko. We are going to be doing some math tonight, once again with cracking the GRE math subject test. This is the second edition of the Princeton review book that is to help students prepare for the graduate record exam. There are a number of people on YouTube, hey YouTube, who have stated that they appreciate that I'm going through the material. I do apologize that I'm not going through it faster. The idea behind this is that we're going to be going through all of the content in this book, which ends right about here. So all of that content remains. And that includes Calc 1, Calc 2, Calc 3, linear algebra, differential equations especially, and then beyond that it also includes some of the other higher math type stuff. Number theory, abstract algebra. There's Zach. Good evening, Zach. Infinite series, you rang? Set theory, combinatorics, probability statistics, point set topology, real analysis, and complex variables. So we will eventually get to all of that stuff. I know if somebody is actually waiting for like specific material, you can contact me here at Twitch anytime you want, or you can comment on a particular video. I'm probably not going to, do an entire section or anything like that. But you want me to do a problem or two from a different section of this book or different section of mathematics entirely? Sure, we can talk. So let me know if that's something you're all interested in, or what you might be, what particular subject you might be interested in. Anybody who is here on a standard Wednesday night, please ask any questions you want. Occasionally, if we get, a little bored of doing GRE stuff, we can start poking around other people's Discord servers and start looking at the questions that people have asked in there. It happens. We might want to actually grab the stylus for the actual thing that we're doing. Alright. Thank you everybody for putting up with me. It's quite wonderful to have you. Right. Let's see. We just started a series on blueprints. So if anybody is interested in watching that, we're doing it on Tuesday nights. Friday is still currently Against the Storm. Once we finish that, we're going to be going on to another long game, probably either Final Fantasy VII Rebirth or, there's a few other long games that we have set up there. On Sundays, we have temporarily discontinued our base building night, so we may end up going there occasionally on Fridays. I am running a TTRPG campaign called Titan's Grave, The Ashes of Volcana, which was run by and written by Will Wheaton and his son Ryan. It's a really great campaign. I'm currently (10, 15 pages deep in lore and backstory, and making sure that I'm trying to stay ahead of the campaign. Currently, I'm working on news reports that they will see while they're in the city. So that's fun. It's definitely stretching my creative side, and I never thought that this would be even remotely a possibility. But yeah, it's actually kind of working. Okay, so Tonight we're looking at infinite series. So first off, we have sequences, which are just lists, and typically of numbers, but it's going to look something to the effect of usually set defined by a sub n, it's going to be equal to, and then we have a list on the other side, which may or may not be in brackets. It kind of depends on who you talk to. A1, A2, A3, etc.
This is the transmitter. You might think it's too random, but full and safe 300,000 volts. Extremely low frequency. One specific frequency. Don't try this yourself.
Okay, infinite series is usually given by the sum as I goes from 1 to infinity. I really should be consistent about this. Most of the time we use subscripts I, J, and K when we're talking about integer, discrete type things like that. You can use N, it's fine. However, we usually prefer doing, or if we want the, well, we'll get into it, but if we want to stop a sequence at some point instead of having an infinite series, usually we let that be N, be the final number that we go to. So typically our I goes from 1 to N, and in this particular case, N is infinity. So this is going to be the sum of all a sub I, which is going to be equal to a sub 1 plus a sub 2 plus a sub 3, etc. Off to infinity. Okay, and again, often we can also express this as the limit, as n goes to infinity, the sum of I going from 1 to n of a sub I. And beyond. I mean, if you do those trans-infinite, is that what that's called? Trans-finite numbers? I've never touched any of that stuff. We also have partial sums, which go from I going from 1 to n, where n is not infinity. So here we have a sub 1 plus a sub 2 plus dot dot dot, all the way out to a sub n minus 1 and oops, nope, plus a sub n. So oftentimes this is something like S1 is going to just be A1. S2 is going to be A1 plus A2. S3 is going to be A1 plus A2 plus A3, etc. So it's going to continue to go on just like this. Alright, S sub n is therefore a sub 1 plus a sub 2 plus dot dot dot, all the way out to a sub n minus 1 plus a sub n. And then this list will continue beyond any particular n. So we can have an infinite partial sum, which is just really the infinite sum. And oftentimes, right, this I express as the limit as n goes to infinity of s sub n. Right, and then this is just as above. Right, so when we have that infinite sum up there, this is really what we need. Okay, so right, if S sub infinity is finite, then the infinite sum that goes from 1 to infinity of a sub I will converge. And if S sub infinity is infinite, then this thing diverges. And really, I guess we should be a little bit more like Zach and say, no, hang on. If S sub infinity has a finite limit. And similarly, going the other way. It has... You know what? Yeah. Nope. That was not an eraser. Right, if S sub infinity has no finite limit, then that series diverges. So an example that's used, take the infinite sum as I goes from 1 to infinity of 1/2 raised to the I. Right, so if I is 1, we get a half. If I is 2, we get 1/4. If I is 3, we get 1/8, 1/16, 1/32, etc. This is then going to continue on forever and ever and ever. So, we want to look at this and say, what about the partial sums? If we have a finite limit to S sub infinity, we could tell probably in a quick manner by looking at the partial sums of these things. So if we go, what's S sub 1, S sub 2, S sub 3? I guess the more appropriate way to say this is n. You want right. Given S sub n, given n, what is S sub n? So if n is 1, we get S sub n is a half. If we get 2, S sub n is going to be 3/4. 3, S sub n is going to be 7/8. And then that is going to continue on and on and on. So we double this, it's going to be 14/16 plus 1/16 gets us 15/16 for 4. So hopefully we can see here, right? This is increasing and becoming 1 unit, whatever unit it is that we have, whatever unit it is that we're adding, we always end up 1 of those units short of a full 1. So as we keep going, we're going to be able to see that, yeah, that is actually true. All right, so this comes out of nowhere. Yeah, they just use a formula. So we're going to derive the formula coming out of here because I am a mathematician after all. We want to be able to at least describe how that is. You may never need it, but it is helpful to see it most times. This also leads into what we're doing in the next section, but it'll be fine. So roughly speaking, what we have is that this is some r to the, I guess we should stick with what we got, r to the I or we could start with a1 times r to the I minus 1 for all of our individual values. So we're going to start with a sub a sub I is going to be equal to. So we start with a value a sub 1, which is always going to be the first element in the sequence. And then we multiply by r, our common ratio between these two values, raised to the I minus 1. So in this particular case, what we have is a1 can be 1/2, and then r equals, what's the ratio between, nope, this is not the right one to do. Of course it's, that's this one. Right, a sub 1, and then compare, this is going to be r equals 1/4 over 1/2, which is 1/2. So a1 is 1/2, and also right, so we get a sub I is going to be equal to a sub 1 times r raised to the I minus 1. So when we go in and say, okay, I want a sub, the sum of some a sub i's, from I going from 1 to n, then what I want is a sub 1 for our first term, plus a sub 1r for our second term, plus a sub 1r squared for our third term here, plus ... As far as we're going to go, which means again here a sub 1 times r to the I, and in this one, it's going to be n minus 1. Right, which is equal to s sub n. Okay, now if we do s sub n minus hang on. Sorry. Right, s sub n minus r times s sub n. What we're going to do here is we're going to say, okay, let's let r times s sub n be, that's going to be our next term, right? Right, so we're effectively finding the difference between them. There's a reason that we do it this way, just, you know. So we get a sub 1 plus a sub 1r plus a sub 1r squared plus dot dot dot, all the way out to a sub 1r to the n minus 1. Then minus r times s sub n is going to be a minus a sub 1 times r, right? R times our first term, a sub 1, minus r times our second term, which was a sub 1r. So now it's going to be a sub 1r squared plus dot dot dot. We're going to go all the way out to a sub 1r to the n minus 1. Oops, minuses. Easy fix. Minus a sub 1 r to the n minus 1 plus 1, right? Because we are adding an extra r to all of these. So that's now going to be a sub 1 r to the n. So when we subtract these, we get only two terms left. A sub 1, this is sort of like the telescoping stuff that we talked about at some point, minus a sub 1 r to the n is equal to s sub n minus r times s sub n. We can take out s sub n, and we're left with 1 minus r. Over here we can take out a sub 1, and we're left with 1 minus r to the n. Now we say, okay, s sub n is going to be equal to a sub 1 times the quantity 1 minus r to the n, all over 1 minus r. So the hypothesis, right, is that our s sub n is going to be equal to, let's see, this was 2 to the n in the denominator and 2 to the n minus 1 in the numerator. Wait. It's not true. What happened here? I mean, we could just cheat and say n has to be greater than or equal to 2, but that's unsatisfying. What happened in the first case? Right, 2 to the 1. Oh, no. Right, 2 to the 1 minus 1. Yeah, no, that's fine. Jeez. I was just trying to do a different 2 to the n, I guess? I don't know what I was thinking. We're good. We don't need a caveat. Right, so this is the thing that we want to get for this particular setup. So now we can look at this and say we have s sub n as a general formula. So let's double check our hypothesis from before and make sure that it actually works. The hypothesis was totally there before, 100%, yep. So s sub n is equal to a sub 1 was a half times 1 minus r is a half raised to the n. I mean, we could just do also n and do it in general over 1 minus a half. Right, so then this is going to be equal to 1 over 2 times 1 minus a half, right? It's just a half down there, which multiplied by 2 is just going to get us 1. And then up top we've got 1 minus a half raised to the n, which is just literally 1 minus 1/2 to the n, or 1 minus 1 over 2 to the n. Well, if we simplify this one over here, we get 2 to the n over 2 to the n is 1 minus 1 over 2 to the n. So these are all squared up now. Got what we want. So this formula is going to work for everything, right? Anytime that you want a finite sum of partial sums of an infinite series, you can use this formula right here. A sub 1 is your first term, r is the ratio, common ratio between any two adjacent terms, and then n is the position you want calculated out to. So sum up all of our a's from a sub 1 out to a sub n. Okay. Then what we want to do is set the limit as n goes to infinity of this stuff. So first of all, if we do this with this limit here, s sub infinity for this particular setup is the limit as n goes to infinity of 1 minus 1 over 2 to the n. And 2 to the n is becoming very, very large very quickly, and then nothing else has an n in it. So this is going to be equal to 1 minus 1 over what is effectively infinity, but, you know, we're not really doing that. We're just saying that, yeah, this sum is going to be, this whole value is going to approach 0 as n gets really, really, really big. Right, s sub infinity is equal to 1. So then we do it in general. So we say, okay, if we want it in general, what do we do? Then this is going to be the infinite sum of all partial sums s sub n. No, the limit of all of our partial sums s sub n is going to be equal to the limit as n goes to infinity of a sub 1 times 1 minus r to the n over 1 minus r. We do have some small problems. So first of all, anything that doesn't have an n in it can just pass right through the limit in the first place. So a sub 1 times the quantity, 1 minus. Here we need the limit because this term has an n in it, r to the n. All over 1 minus r. No n's anywhere else to be found. So we have a sub 1 times 1 minus something all over 1 minus r. So here we have to take a little bit of stock of what we have. R has not been told to us to be anything in particular. So we could have any number we want plugged in for r. But the problem here is going to be that we have different classes of sums at this point. Right, so if r is greater than 1, then a sum of infinite ones, or sorry, a sum of infinite numbers that are going off to infinity are going to go off to infinity. So as r gets really, really big, doesn't even have to be big. If r is greater than or equal to 1, then we're going to have an infinite number of numbers that are 1 or bigger getting added together. So it's going to be an infinite value. So this will diverge. And even if it's going to end up being alternating signs, because if r is negative, we could also say, okay, well, if r is negative, then one term is going to increase some, then the next term is going to decrease some, and then the next term is going to increase some, the next term is going to decrease some, but they're going to add together in an amplified sort of way. Those numbers are going to get bigger and bigger and bigger, and the swings are going to get more and more wild as we keep going. So if the absolute value of r is greater than or equal to 1, then this series diverges and we can't do this. If the absolute value of r is equals 0, then we don't have an infinite series in the first place. You've just multiplied by something and gotten 0 for the rest of all time. So right, so if r is equal to 0, and it doesn't need an absolute value, but if r is equal to 0, why are we even here? Right? That's not really an exponential function, so we don't need to do all this. And the only other interesting case is what happens when r is between 0 and 1 exclusive. And again, that's the absolute value of r. So we're allowed to have negative values as well. All right, if r, the absolute value of r, is anywhere between 0 and 1 exclusive, then this series will converge. And in fact, we're not even looking at the whole series at the moment. We're looking at the limit as n goes to infinity of r to the n. Right? All of this will diverge if absolute value of r is greater than or equal to 1. Again, same deal here. That really? Okay. Apparently doing something completely different. Nope. It's alright. There we go. Then this limit as n goes to infinity of r to the n will converge. So r to the n, as n gets really big, if r is a small number, will become even smaller. And specifically, right, limit n goes to infinity of r to the n is going to be equal to 0 under this particular case. So we have an interesting case here. It's the only one that's interesting. A sub 1 times 1 minus 0 over 1 minus r. So this means that the s sub infinity asterisk, right, this is only on series that actually converge. We end up with a1 over 1 minus r. Right, as long as this thing converges, we're good. I think we're going to have to stand up at the desk. Let's see. Nice. Cool. It's even slightly low. That's alright. Yeah, I think that works. It's a little bit in the shadow, but it's alright. Okay, so S sub infinity is going to get us a sub 1 over 1 minus r, as long as that limit, as n goes to infinity, of r to the n is going to converge. Right. So in this particular case, we now have a shortcut to get. Good evening and welcome. Thank you for the follow. S sub infinity 4 a sub I equals 1/2 raised to the n I. Knew it. TikTok, how's it going? S sub infinity is going to be, we had here a sub 1 was 1/2 over 1 minus r was 1/2. This is a nice easy one to calculate. We already did it up above anyway, but we might as well just look at it real quick. It's 1/2 over 1 minus 1/2 is 1/2, so that's equal to 1. We're looking at the Calc 2 stuff on infinite series. So just getting through the preliminary stuff of talking about infinite sums, partial sums, and the partial sum formulas that get us the finite and infinite series, or finite and infinite sums. So we've gone through all that, which is really just pre-calc for me. I mean, it was in my pre-calculus class. So that's super easy stuff. One would hope. And then oh yeah, this was also a thing that somebody came up with at some point, was like, oh, well, we can use the geometric series, or in our case, the infinite series sum formula of a sub 1 over 1 minus r to figure out a particular math problem, which ended up being the sum of all integers being equal to negative 1/12 or something like that. They like figured out a way to simplify it so that it ended up being that. And it's one of those things that really aggravates me, because they're using the formula improperly. If you look at it, right, the r that this particular person was using was in fact greater than 1, or the absolute value was greater than 1. So clearly, right, that doesn't work. You're not allowed to do it. You're breaking the rules of this particular formula in the first place. So you can't use the infinite sum formula unless you have an absolute value of r that is less than 1. I'm going to have to look that one up again. But I think it was the number file video where the sum of all integers is equal to negative 1/12. So if anybody wants to see that, it's out there. And it bothered. No, I mean, it's okay. All right. The sum of a convergent series depends on which terms are included. So we can start the value of the index of n at any particular value. This is just basically saying that we're allowed to say, well, I can start from the I index can start from 0 and go off to infinity. That doesn't matter. The only thing that's going to affect the actual value is what term this is overall. So if I say a sub I, where I is going from 0 to infinity, I can't then include all the way back up here. I can't then include, oh, this is just 1/2 raised to the I, and expect to get the same value. It's not going to work, right? In order to get the same value, this first term has to be the same. So I would need a first term that is still going to be 1/2. So if we want the same value, and here we're starting with an index of 0 instead of 1, a sub I is going to have to be 1 times r to the I. So that here, nope. Sorry, no. R to the I is going to have to be 1/2 still. That's not happening if I is starting at 0. Nope. This is going to have to be 1. It's been forced by the index that we're using. So therefore, the other part of it has to be 1/2 in order to make sure that we get knocked down to the right level. Okay, so like this one will work. Or we could go the other way and say, okay, I want a sub I. Nah, that's all right. There's a few different ways of doing things. Just make sure that your terms all end up being the same values as you go through. Once you get that, then everything works out pretty nicely. Okay. List below gives some of the most common and useful convergence tests for infinite series. So, easy one, right? If the sum of a sub I, and very implicitly here, this is going to be I goes from 1 to infinity without actually writing it. Sometimes they'll just put sum a sub I. Oh, the term, jeez. Go like this. if the terms of this particular infinite sum do not approach 0 as n approaches infinity, then the sum of a sub I does not converge. Right, so this is an easy one to just look at. If we want the sum as I goes from 1 to infinity of 2 to the n. Nope, 2 to the I. I'm going to do that all night. 2 to the I. Then we know that this is going to diverge. Since a sub n is equal to 2 to the n, and then if we take the limit as n goes to infinity, this does not equal to 0. Hey, Math Fun, how's it going? Got an itchy back at the moment. Things are going alright. Starting to work our way in on convergence tests for infinite series, so this will be fun. Right, so the first one is just testing for divergence. So basically, all it does is say, look, if your terms don't go to 0, then the infinite sum can't go to 0. It's not possible. Alright, no, that's not it. Then the infinite sum can't converge to a specific value. It must diverge. And we'll just misspeak the whole time, it's fine. Nobody needs it, right? Okay, technically, the next one's about the linearity of convergence, but it doesn't actually say that necessarily all the way through. I'm sure that there is another... Yeah, it's actually 2 and 3, but yeah, we'll combine them. It's fine. So, in linearity, the first thing that we have in order for something to be a linear operator or anything like that, what we've got is if we've got two infinite series, right? Assume that we have the sum, infinite sum of a sub I and the infinite sum of b sub I. You know what? Let's separate this. Assume that they converge. To A and B respectively. Then what's going to what's going to happen here is that any linear combination of the series are going to end up resulting in a linear combination of their individual results. So the sum of it's all right. Case of A, sure, why not? Times, this is not confusing at all, it's fine. Times A sub I, plus or minus the sum of K sub B times B sub I is going to be the same as K sub A times the sum of A sub I, plus or minus K sub B times the sum of B sub I, which is going to be equal to K sub A times capital A, plus or minus K sub B times capital B. Right, if either the sum of all A sub I or the sum of all B sub I diverge, then our linear combination K sub A times A sub I plus or minus sum K sub B times B sub I diverges for all K sub A, K sub B, K sub B. Not being equal to 0. Can you hate conditional convergence? You can. That's a very different statement. Yeah. I'm not opposed to it. There's also, right, A sub I. Sum of all A sub I plus or minus the sum of all B sub I are also going to be the sum of all A sub I plus or minus B sub I. And yeah, if they both converge, then they converge to this other thing, which is going to be probably some easier way to find out what it is. Alright, for P series, this is anything that looks like the sum of was it n? Yeah. 1 over n to the p, or in the case of what we have been working with, I to the p, which is one of the reasons why I start questioning the wisdom of what I'm doing here. Right, converges for all p greater than 1. And that is and diverges for all p less than or equal to 1. Right, no caveats on that at all whatsoever. P is any real number at this point. Right, it's not well defined to work on the complex numbers or anything like that, so wouldn't be able to do it anyway. However, right, any p in the entire real number system, 1 over I, which is again your index, so we're just adding up all of our individual fractions. 1 over 1 plus 1 over 2 plus 1 over 3, but each of those numbers are now going to be raised to the p power. And as long as it is greater than 1, so 1 over I to the 1.000000001 will converge. Whereas 1 over I to the 0.9999999 will diverge. Very slowly, yes. And negative numbers just flip it up to the top anyway, and then you've got an exponential function. So these are still exponential type functions, but nonetheless. All right. Let's see. So I like to call this one comparison or direct comparison. So here what we're doing is we're going to say that we have two particular sequences, A sub I and B sub I. Then what's going to happen is we're going to get something that, if we were to look at it as if it were a function, right? I'll just pretend for the moment. This is going to be f of x, and this is going to be g of x. Or at least the representation is such that those are, you know, discrete versions of those functions. Then what we're doing is we're saying, okay, we've got stuff that looks like this. And again, they're all going to be greater than 0 forever. If A sub I is always lower than B sub I, then you will be able to tell if B sub I is able to hold in A sub I. So if B sub I converges, then A sub I must also converge because it's always smaller. We're about to go to adds, so it'll jump out in like 2 seconds, I'm sure. Right, so if A sub I, nope, already broke it. If B sub I converges? Some. There it is. Okay. We'll be right... Ow. We'll be right back. Thank you, everybody, for coming. And... gonna hop out. Grab a drink or something. Stretch. Stand up. Sit down. Fight, fight, fight. We'll be back in 3 minutes. And we'll do some Tai Chi, because I learned something new today. Alright, 3 minutes. So we learned something new in Tai Chi today. Gotta show it off, right? Or rather, gotta practice it multiple times so that it sticks. My instructor has been taken to being like, this is actually really good. It's quite amazing. I'm like, I know. I actually practice like 3 or 4 times a week. I don't tell him that I do it to an audience, but you know. So, basic warm-up exercises. You start out basically kind of like a windmill, but instead of allowing your arms to just kind of fly out, we kind of, as we're coming across, we kind of whip downward a little bit. And more or less, you want this to be able to do its own sort of thing. So your arms are going to kind of not go flying all over the place. They're not going to go... I need to switch scenes. Some people actually might want to see this. I don't know why, but whatever. I'm not going to judge. If you do have Tai Chi people nearby, I do recommend, anybody over 40 especially, it's much gentler. However, I am doing Tai Chi Chuan, which is the more combative side of the art, so it can be pretty rough if you're not used to it. But if you have another martial art under your belt at some point in your life, it's a good one to pick up. And it oftentimes ends up being like doing slow stuff, which can also help. Also helps you find where your center of energy is and try and use your it's called the inguinal crease, which is that spot between your thigh and your abdomen, right in like along that crease here where the groin is. You basically try and sink into that little space, and then like it acts like a spring-ish, where you can kind of store energy and then come out of it real fast. Alright, so then we do sort of like a Nordic skiing type of thing. We're not trying to like use our arms at all. So the point of this is to just basically use your hips and essentially make your arms move on their own. And you're only going to guide them in order to prevent injury. So you don't want your arms to like flop, because that's really bad. But let them kind of go where they may. You're just gonna kind of do this for a bit. Warms up all of the joints. Make sure the synovial fluid's all spread out and you're not going to hurt yourself doing something like that. Right, and then we can go 1 foot forward. And remember, just like you were trying to do on the swings when you were a kid, right? Get higher and higher without ending up going slack. This is one that oftentimes I hear large amounts of popping in my shoulders. So I know that the air is getting out of there. Don't do something if it hurts. Hashtag never medical advice. And then switch, which really doesn't do much, but you know, stay symmetric. Ooh. Looks like my cord to my monitor is pulling pretty hard, so I may need to lower that a couple inches. Or just put the power cord on a pedestal. Right, so then we get in the position, put both feet forward, and we kind of pull the body upward. Oftentimes it's said like as if hanging by a string through your head and your spine. Let everything else just kind of hang down. And then we get the arms out a little bit. And we turn one way and then back toward the other hip. And then we turn and we go back toward the other hip. And we do this. Oftentimes slower, but you know, try to get on with it. Oh no. What am I missing? Nope. Okay, that was just me. Miss seeing exactly where the redeem was. It's alright. Alright, then once we get comfortable with doing the bear, we tend to bring hands into it. So one comes up as the other one is down, and then we swap. Probably hear my shoulders popping. Right, so come down, the other side comes up as we start moving the other way. Turn, and again, arm comes up as we start moving the other way. And then repeat one and the other. We're using this like sort of energy ball analogy to do all this. You usually want to lead with the back of your forearm though. Right, and then there's others that are mostly like lead with the hand while the other one is down, either low or backwards, to serve as like a guide. Okay, and then I have learned basically the first third of the form. I don't even think I'm quite there yet, but put the feet together out in a V shape. What we do is we start in bear, tuck to the right, step left, straighten feet. We want to make sure that they're straight, and then we go breathe in and then out. Right from here, we tuck into the left-hand side here and bring the energy ball while turning on the heel of our right foot to get that like kind of stereotypical Tai Chi pose. Lean forward, step out, do a ward off to this side, straighten the back foot, 45 degrees or so, and then the back arm just comes out to about here. I might have enough room. We'll see how it goes. This tucks into this side again. We do a turn on the ball of the foot and step out. Lean into a ward off. Turn with the back. Turn with the heel of the back foot. Then roll back. Press. Push. Lean back. Arm still out. And then we have to turn on the heel of the front foot, which is going to whip us into this really weird pigeon-toed stance. We then tuck we're tucking into the front leg, come down like this, plucking as if plucking something out of your hand, lean back on the back leg, and twist the other way while doing a single whip. And then we bring all this out here, and then turn, lean, and turn the back foot all at the same time. From here, this comes down a little bit, and then moves into a, where am I? Here we go. Kind of blocking with our hands stance here, where all of my weight is on my back foot. The front foot is basically only there for balance. My left hand is about even with my forearm to elbow of the other, and this one's up near like my head-ish. Okay, and then from here, we drop everything down and come in for a shoulder strike. So this is coming in like this. This is going to be even about here just to make sure we block anything that's coming at us. And then the next step, I I literally did this today. Yeah, okay. Next step is that we lean in to the right side, pick up the left foot. This is going to come out and touch toes to the ground. And then we're going to do, I forget exactly what it's called, but it's like the crane fanning its feathers, essentially. So this comes up like this. Oops, nope. Messed it up already. This one comes down, this one comes up. So it's essentially like this. What we're trying to do is, it was described to me like somebody's coming at you to try and press your shoulder and your hip at the same time. So if they go like this, then you don't have a whole lot of like area to respond with. If somebody actually does push you in both of these places at the same time, you're probably going over. And especially if they hook your leg on theirs, then if they push you at these two locations, like it's basically creating a line going across your body where all that force is going to be imparted. So if somebody comes in like that and does a push this way, that's going to be a problem. So you come in, wow, you come in from here and go like that. It's going to stop this coming down, block the thing that's coming at your hip. This is going to come up and block the thing that's coming at your shoulder. So then we turn both hands about 45 degrees out as well. So coming from here, we're going to go to here. That's much better. I forget exactly what he called it. It was something to the effect of like crane fanning its feathers, because he actually said he went to Malaysia to go study under like one of the masters, and he actually saw cranes that were sitting there like this in the water, or standing, I guess, pretty much on one leg, and then their upper wing was open, allowing air and or water flow underneath here to cool them off, and then the other one's out down here, which I don't know exactly why they do that, but maybe balance, maybe something else. Seemed really cool. All right, thank you everybody for humoring me. Gotta get some level of fitness around here. Okay. So we're going to do the comparison. So if b sub I is always greater right, so like b sub I is equal to g sub x for all, or like sum b sub I is equal to g sub x for all x equals I belonging to the positive integers. It's natural numbers if you want, something like that. All right, and similarly the other way for A and F. All right, these values are going to be here. They don't always have to be the same distance, but they're always going to be one greater than the other. So if the sum of b sub I is going to converge, and a sub I is always smaller for every individual value of a sub I compared to b sub I, then that's going to say for us that the sum of a sub I converges. And if going the other way, the sum of a sub I diverges. Then the sum of b sub I diverges. And, super important, all other combinations are inconclusive. So again, the way that this works is if a sub I is smaller and b sub I converges, then there's no possible way for a sub I to escape, to diverge. Similarly, if a sub I is always smaller and diverges, then there's no way for b sub I to be contained. So think of it like that. Right? A sub I could always be contained if b sub I is also contained. And then b sub I can only not be contained if, well, that's not, no, hang on. We can only prove that b sub I cannot be contained if a sub I cannot be contained. So think through all of the possible combinations, right? What if the sum of b sub I converges? What could we possibly prove? Well, can a sub I converge? Can a sub I diverge? Go the other way. If we know that a sub I diverges, then what does that say about a b sub I? Is it going to converge? Is it going to diverge? If a sub I converges, does that say anything about b sub I? If b sub I diverges, does that say anything about a sub I? So try and like break these down and think about every possible combination. And then you say, well, there's only the two here that are actually going to be conclusive. The others, well, we just don't know. Okay. Right, and the other thing is that it doesn't always have to do that. So it could be, for instance, that our a sub I could very well go like this instead. This only has to be true for all values of n that are greater than or equal to some theoretical value capital N. So in this particular case, that capital N is at the intersection point of these two functions. And our first n that is considered is going to be this one right here. Right, that's going to be our lowercase n first one that we pick. Okay, we also have the ratio test. All terms are going to be non-negative. We want to know what the limit is of n going to infinity. Right, find the limit as n goes to infinity of a sub n I. A sub I plus 1 all over a sub I.
Invincible.
Right, call that L. So if the limit L is less than 1, sum of all a sub I converges. L is greater than 1, sum of all a sub I diverges. And that includes infinity. So we're going to call infinity a thing that you can call greater than 1. And L equals 1 inconclusive. So for this one, if we had something like, well, we'll do like all of them basically. 7. The root test is going to be more or less similar. All right. Given a series, sum a sub I of non-negative terms. We're going to do the same thing, find limit as n goes to infinity. This time though, we're going to take the nth root of a sub I and set that equal to L in much the same way we did up there. And guess what? That's right. We're just going to copy paste this bad boy because we can do that. given a series, in this case sum of a sub I, such that sum f of x is equal to a sub I, f of I equals a sub I. It's a nice shortcut. For all I belonging to positive integers, and f of x is, I guess that should be defined first, but whatever, monotonically decreasing for all x greater than or equal to 1. Right, then we have I goes from 1 to infinity. Take the sum of all a sub I is going to be yeah, okay. Will converge if and only if the integral from 1 to infinity of the continuous function f of x dx converges. Okay. So all these different tests really are mostly a matter of what do I want to use, what's common sense for this particular one. So A, for example, we're taking the sum I goes from 1 to infinity of sine squared of I over I cubed plus I. Right, what do we want to do with this? Well, sine squared is always going to be between 0 and 1. So I would like to do a direct comparison. And I would like to do a direct comparison to the sum as I goes from 1 to infinity of. Now, what do I suspect is going to happen? Well, this having a cubic in the denominator, I suspect that this is going to converge. Now, right, we could compare this, for example, to a p-series, 1 over I cubed. Which converges. So we have to first, let's call this a sub I equals this stuff. No. Sum of a sub I is that stuff. Sum of b sub I is going to be that one. So first of all, right, series b sub I converges via p series. Well, if it converges, then we need to find out whether this is always going to be greater than the original function we had, sine squared of I over I cubed plus I. So assert, we'll try to find b sub I always greater than or equal to a sub I for all I. Does it have to be greater than a specific value or specific individual? Yes. I greater than or equal to some n value, whatever that is. So I'm just going to pick 2. It doesn't really matter. 1 would probably be fine. 1 would probably suffice. So we're going to say that, okay, b sub I is going to be, let n equal 2. This is going to be 1 over 2 cubed is greater than or equal to the sine squared of 2 divided by 2 cubed plus 2. Okay, so here, number of ways we could do this. Essentially, what we want is, just drop something. There are a number of ways we can do this. One would be something like, okay, make this 2 cubed plus 2 divided by 2 cubed. Is this going to be greater than or equal to sine squared of 2 over 1? Right, we can multiply both sides by 2 cubed plus 2, which is 10. Right, 10 over 8, well, okay, 5/4. Is 5/4, well, we know that 5/4 is greater than or equal to 1, which must be greater than or equal to a sine squared. So yes, it works for this one. But using the same logic, we can actually prove that this always is true. By saying that this is now going to be 1 over 2 to the n. Well, okay. Fine, we'll use lowercase n for this one, because really we're talking about for all possible n that are greater than or equal to the capital N. So we do this and we say, okay, 1 over 2 to the n needs to be greater than or equal to the sine squared of n over 2 to the n plus n, right? I went backwards on this. No, n cubed. N cubed. Right, this is backwards. N cubed must be greater than or equal to sine squared of n over n cubed plus n. Again, do the same thing. N cubed plus n is always going to be positive for all of our n values greater than or equal to 2. So we don't have to worry about negatives or anything like that, trying to flip our sign. So this is just going to be n cubed plus n over n cubed. Must be greater than or equal to the sine squared of n. Well, again, this is going to get us 1 plus n over n cubed is 1 over n squared. Must be greater than or equal to, question mark. Okay, 1 is 1 plus 1 over n squared will always be greater than or equal to 1 for any value of n greater than or equal to 2. And that is going to be greater than or equal to all possible sine squared values. Can never get a sine value, a sine function value, which is going to be greater than 1. It just never happens. So here, we know that this is going to work. So here, we could say that based on this, this implies that the sum, as I goes from 1 to infinity, of sine squared of I divided by I cubed plus I also converges. So again, what we did here was we said, okay, we've got this like complicated series that we're looking at. We want to say at its heart, we need to find a simple series, which is going to then, if we suspect that this thing, whatever it is, will converge, then we need to find another series which converges and is bigger than our target series, the one we're trying to prove. Find a bigger series which converges, and therefore it must contain, it must hold back, it must hold in the target series. So in this case, we picked the series, infinite series, I goes from 1 to infinity of 1 over I cubed. So then we say, okay, that converges because it's a p series. It's I to the 1 over I to the p. We're taking an infinite series of that. Then we say, okay, now we need to show that the individual values that we get in the series every single time have some value beyond which they will always have this particular pattern, that our known series is larger than our unknown series. And if the known series is contained, then the lower series here, our target series, must also be contained, must also converge. So here we said that our p series needs to be greater than or equal to the sine over n cubed plus n series. So all of the individual terms, going all the way out to forever, must always be greater than our sine series, the individual sine series terms. So p series terms must be greater than or equal to the target series terms. And then we multiply by this number because that's always positive in the positive numbers. We got this thing over here, which makes it 1 plus 1 over n squared. And on this side, we're just left with sine squared of n. Sine squared of n must be less than or equal to a value of 1. Must also be greater than or equal to 0, but that's not important. Right? What we care about is that this is less than or equal to 1. At the same time, we know that 1 plus something with positive numbers in it must be greater than or equal to 1. So now we can stick that 1 in between and say, look, we can compare both of these things to 1, so now we can compare them to each other. So this is saying that our sign value is always going to be less than or equal to this fraction, no matter what we do, and therefore when we walk it back up, this sine squared of n over nq plus n must be less than or equal to 1 over n cubed for all possible values of n which are positive. Which again, now that we've implied, or now that we've found, that all of the individual terms of this thing are lower than a known convergent series, and, yeah, all values are lower than a known convergent series, then this also must converge. It's hard to word everything, so don't feel bad if you don't get it the first 1,000 times. Alright, B. Take the series I goes from 1 to infinity of 1 over square root n plus 3. Yep. Alright. You might be tempted to do this in a number of different ways. The problem is, if you try to do a... You might think ratio test would be pretty nice. The problem is that here, if you do a ratio test, you're going to get the square root of n plus 3 divided by the square root of n plus 4. And if you take a limit going out to infinity, that is essentially 1. So our limit value is 1, which means that the root test, or the ratio test, is going to be inconclusive. If you try to do the root test, I believe you run into the same problem. We could try, but... Right, n goes to infinity. We just take the 1 over nth root. So well, nth root. So this is going to be 1 over n here of 1 over parentheses n plus 3 raised to the 1/2. So now it's just that over 2n. And now you've got limit n goes to infinity of 1 over parentheses n plus 3 raised to the 1 over 2n. Cool. So now what? Right, this becomes another problem, which in theory you can solve. Right, we could do this via if L equals this thing, then the natural log of L equals, and then we can keep working on this. I don't think it's worthwhile, but, you know. Yeah. Let's take all those, turn it a different color, just so that we're keeping track of what's what. Alright, this would be natural log of 1 minus 1 over 2n, natural log of n plus 3. In theory, you could potentially work this out. I think this is going to be 0. Okay, we cannot take another natural log because this is negative. we could, in theory, bring that negative in, make it 1 over n plus 3 inside of the natural log. This would make this natural log of limit n goes to infinity. Let's just reverse those. So otherwise that's just going to be gross. Okay. Natural log of, that could make it 1 over 2n plus natural log of the natural log of 1 over n plus 3. In theory, yeah, this causes a problem, because here the natural log of 1 over n plus 3 is going to, well, the interior stuff is going to 0, which makes that natural log go to negative infinity, which means that the natural log of negative infinity doesn't exist. So we're not able to do this at all. So let's just take this out. Oh man. It's fine. It's fine, it's fine, it's fine. That's where it came from. Okay. So, all that's far too complicated. Instead of trying the ratio or the root test, we could also do a direct comparison again. P series, which is going to be 1 over n to the 1/2, which diverges. Right, so if 1 over 1 to the 1/2 is going to diverge, then what we need, again, looking at the diagram that we drew earlier, what we need is for our P series which diverges, we need the other series, our target series, to always be larger than this thing. Right, 1 over square root n plus 3 is greater than or equal to P series, whatever it is. So in this case, we've got 1 over the square root of n. Is that true? So we're adding numbers to a denominator, which means that this is going to cause this to be smaller than 1 over root n. So this is not going to work for us. However, what we can do is we can say, you know what? We're going to take this function, and now instead of trying to shift it like the +3 is doing, we could take this and multiply it by 1/10. Right, now I'm just doing that mostly for a little bit of fun there, because, you know, we're just going to pick a big number. It doesn't even matter what it is. Make it 1,000. Who cares? If we can prove that this stuff is always going to be less than this stuff, then we end up with a divergent, known divergent series, and this coefficient out in front doesn't change that. It still diverges. And now we're just making it smaller so that we can show that the other one also has to diverge. So if we do this, again, we can multiply both sides by 10 over root n, or we could multiply both sides by 10, not over, 10 root n, or multiply both sides by 10 and root n plus 3. That's actually a better way to go. So we get 10 over here, greater than or equal to root n plus 3 over root n. I think we got it. Ah, that's supposed to be an I back here. Boo. Come on, OB, you know better. I erased the one. Right? Need to prove that this is true for some, and no, for all n greater than or equal to some n, whatever that n is. We don't know what it is, but we can make it up. So in this case, we're just solving. All right, 10 is going to be greater than or equal to. Here, we can combine into 1 plus 3 over n. Well, if n is very small, we could, in theory, find out where it is equal to 100, right? Where the interior stuff is going to be equal to 100. Right? That means that n is going to be like between 0 and 1. So 10 is going to be greater than or equal to all of this stuff for all n greater than or equal to 1. Right? And if you want to rigorously show it, you can show it. You could say, okay, square both sides, and end up with 100 being greater than or equal to 1 plus 3 over n. Then it's going to be 99 is greater than or equal to 3 over n. And then we can say that this is going to be n is greater than or equal to 3 over 99. So n must be greater than or equal to 1/33. So, again, n belonging to positive integers. It's always going to work. All right. Be back in 3 minutes. Get up, stretch, get some water, do whatever you need to, and we'll be back. Thanks for coming. Always my least favorite part, but I gotta do it to myself. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 15, 20. Right out. Right, oh, welcome back. Right. So we just proved here that, right, let n equal 1 is going to be sufficient to get us for all possible lowercase n values greater than or equal to 1. We're going to have that this series, 1 over 10 root n, will be smaller than this series over here, 1 over root n plus 3. Since all of the root n series are now going to be lower than 1 over root n plus 3, and since we know that 1 over 10 root n diverges by p-series, because our p-value is going to be less than 1, or equal to, I guess, but in this case it's just less than. So with those two pieces of information combined, we know for a fact that this one now will diverge. Right, since since the values of 1 over 10 root n are less than or equal to I. We could do either one. Less than or equal to the other one. 1 over root n plus 3 for all n greater than or equal to 1, and the sum of 1 over 10 root n diverges. The sum of 1 over square root n plus 3 must also diverge. Awesome. All right, anybody have any questions on that? Let me know. C. Summation 1 to infinity of I to the 2000. Right. C. I goes from 1 to infinity of I to the 2000 over What is this? I factorial. Ugh. It's not just a turned over I promise. Right? So for this one, we're going to want to do the ratio test. Or at least try it first. We've got different stuff going on here. So we've got a power, and we've also got a factorial. So given that these are two kind of like different kinds of functions, it's going to be a lot easier to figure out what's going to happen. So we want to take the limit as n goes to infinity of a sub n plus 1 over a sub n, which is the limit as n goes to infinity. Right, we call that L our limit. This is going to be I plus 1 raised to the 2000 over parentheses I plus 1, oh no, n. Right, I did it this time. N plus 1 factorial. All divided by a sub n, which is just n raised to the 2000 over n factorial. Okay, so get rid of the compound fraction by multiplying both top and bottom by both the n plus 1 factorial and n factorial terms. And that leaves us with parentheses n plus 1 to the 2000. Ugh. Times n factorial over n to the 2000 times parentheses n plus 1 factorial. Right, so limit as n goes to infinity of n plus 1 to the 2000 over n to the 2000 is going to get multiplied by the limit as n goes to infinity of n factorial over n plus 1 factorial. Right? This is another way to do it. Separate out the like terms and then determine what's happening with each of them. So as we go, limit n goes to infinity of n plus 1 raised to the 2000 over n to the 2000, the number that you're raising to the 2000th power isn't going to make much of a difference. Right? If you remember, as our x values in the x to the p functions, like continuous functions, as x gets really, really big, the only thing that's going to matter is the highest term in the polynomial. Everything else is going to get wiped out. And like if you need to see it, right, this is going to be a little caveat over here, right? This is going to be a, well, certainly not binomial. Well, no, it's a binomial distribution at the 2000th row of the Lewy triangle, also known as Pascal triangle. You're going to get n to the 2000 plus 2000 n to the 1999 times 1 plus, and then we're going to keep going from here until we end up all the way back with 1 on the very, very, very end. Right? If we divide by n to the 2000, then we're going to end up with 1 plus 2000 over n plus all this other stuff plus 1 over n to the 2000. And the limit as n goes to infinity of all of this stuff is going to be equal to just 1. Right? The only term that's going to matter is that one right there. All the rest of them are dropping to 0, and some quicker than others, obviously. So over here, we look at this and we say, okay, this thing has a limit of 1. And the other one, our factorial, does not. Because what we have is the limit as n goes to infinity of, right, what is factorial? Well, factorial is n times n minus 1 times n minus 2 times ... all the way down to 2 and 1. Right? And then we just divide it by n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 times ... all the way down to 2 and 1 as the final digit. Well, that just eliminated a whole bunch of stuff. These are all 1. And now all we're left with is 1 over n plus 1. As n goes to infinity, 1 over n plus 1 is going to go to 0. So now we've got a 1 times a 0. That's going to be a 0. So this states that now, because L got us a low value, i.e. less than 1, I think it was, L equals 0, which is less than 1, so that means that the sum of n to the 2000, no, I, n being some particular value, I being the generic index. Sum of I going from 1 to infinity of I to the 2000 over I factorial converges. Okay. Do D, which is summation I goes from 1 to infinity of I cubed divided by log, or natural log of 3 raised to the ith power. I think ratio is going to work well here. So our L is going to be equal to, we need n plus 1 to the third over natural log of 3 raised to the n plus 1 divided by n to the third over natural log of 3 raised to the n. My other thought was, oh, we could probably use a root test. But the thing with the root test here is that if you're trying to take the root of n raised to a power, it's not going to come out very nice. Like, it's fine. It'll come out to a value. You could then evaluate what that is. And I think because it's going to be a constant, probably e or something similar. The other one's going to show us that, like, what value we're going to get here. Okay, multiply both top and bottom by our natural log terms again. And just like we did in the other one, right? Multiply both top and bottom by the sub-denominators. So all of these compound fractions have got to go. So n plus 1 raised to the third. We need to take the limit because I forgot to write it. Limit, and goes to infinity. Okay, there we go. N plus 1 to the third divided by n to the third times also the limit, not natural log, also the limit as n goes to infinity of natural log of 3 raised to the n over natural log of 3 raised to the n plus 1. All right, as before, right, a power which has the same exponent, top and bottom, is just going to get us the ratio of their coefficients, which is going to be 1. Times limit as n goes to infinity. Looking at these, we have the exact same thing, both top and bottom, except at this point, right, we have natural log of 3 multiplied n times divided by natural log of 3 multiplied n plus 1 times. So we have one extra natural log of 3 in the denominator. Natural log of 3 is going to be greater than 1, which means that the fraction is going to be less than 1. So the summation I goes from 1 to infinity of I to the third over natural log 3 all raised to the I converges by ratio test. E. Summation I goes from 1 to infinity of natural log of I over I squared. Alright, so again, we could compare this to something else. So I suspect that this will converge, because the type of function on the top is smaller than the type of function on the bottom. Even a natural log divided by I raised to the 1.000000001 should eventually still go off to should go off to 0 and converge. In theory. To that end, we don't want to do the ratio test, because we're going to end up with effectively 1. I don't know if we can take... No, we don't want to take root test. Root test is mostly for tower functions, so where you have, or an exponential function, where you have variables in your exponents. So, let's see. Guess we could try it. I don't like it. Alright, so what did we do? We did comparison, we did p-series. This is not going to be p-series. You can't compare natural logs to p's, at least not directly. We could, in theory, show that just the natural log diverges, but that's not, it's no fun. But what we care about is that the p-series, or the natural log, is then divided by an actual p-series here. Excuse me. Okay, so we need something that's always going to be bigger than that. Or at least after a certain point, it's always going to be bigger. And we need to prove that. Okay, so let's try. X over x squared. Okay, so this is the function we want to look at. Let's go from x equals, like -1 to 100. And our y-axis is going to go from like -0.1 to +0.2. Okay. Okay, so 1 over x is pretty much always just going to be bigger than that, so this is not a problem. We're just not going to use it, right? if we did... Hey, Famished, how's it going? If we did 1 over x, right, it's over the top of it. So we'd be looking to contain our red function. But the problem is that 1 over x is the harmonic series, which does not converge. Right? By p-series, it's, n to the first. So our p-series makes that fail. However, if we did something like 1.01 at some point... Hey, there we go. We'd have to show here, for instance, that 1.9... that's not going to work, is it? Nope, that's not going to work. Because eventually this is going to meet. I may not know where, but, Oh, furthermore, that's an issue, because if... Actually, right? That was the point. If we did 1.1, and we could show that this is always bigger than and converges, then we're better off. I don't know if we can do that, but... Linear equations in 2 variables, nice. Alright. So we want to show, right, which converges via p-series. So that means we want 1 over n to the 1.1 to always be greater than or equal to natural log of n over n squared for all n greater than or equal to some value big N, whatever that is. Okay. Yeah, I think it's doable. So, as psychotic as this might be. So if we multiply by n squared on both sides, this is going to be n to the 0.9, which needs to be greater than or equal to the natural log of n for some particular n value, or for all n greater than a particular n value. If we raise e to both sides, this is just going to make a mess. Right, we're never going to get n just by itself, which is a potential problem. This is an exponential, though. think this does make it a little more obvious, though. So if we go home here, and we get rid of both of these, now the equations we want to compare are just y equals x. And then e to the x to the 0.9. Yep. So how do we prove it? Other than, right, there is no intersection point, as far as we know. Yeah. It's just a different class of functions, really. If I try to raise it to something that's just going to multiply powers by powers, not raise powers to powers. So that doesn't help. Alright, if we let n to the 0.9 be equal to m, then n is equal to 0.9 is 9 over 10. It's going to be m to the 10/9. So essentially what we've got then is e to the m greater than or equal to m to the 10/9, which is true. Right, and then we can compare those as well. So this is going to be e to the x compared again to x to the 10/9. Which is true for all values in positive x's. Awesome. Right, so that's going to roll back to all those other statements and say that, yep, those are all the same too. So all of these things are true, which means that this statement right here is also true. So our comparison, which converges, is always going to be greater than the unknown natural log over I squared series. So every single term in the positive integers is going to have that relationship. So therefore, right, since 1 over n to the 1.1 is greater than or equal to natural log of n over n squared for all n in positive integers. Hey, Pen. Good evening and welcome, everybody. My name is Obi-Wan Piz. This is nSimplex Pachinko. We are doing a bit of GRE prep. So if anybody is doing the graduate record exam, we'll be happy to help. For right now, we're trying to figure out some series comparison tests, which is everybody's favorite part of Calculus 2. Alright, since 1 over n to the 1.1 is greater than or equal to natural log of n over series of unfortunate events. Very true, Hamilton in dynamics. Natural log of n over n squared for all n in the positive integers. And since sum of 1 over I to the 1.1 converges. There it is.
I have a pen. I have an apple. Apple pen.
It's a raid. Thank you so much, Pen. Coming on in. Bringing everybody over. Okay, so since we found out that, like, the comparison sequences always have this particular relationship, and, right, our tested, known convergent series is now always above the one we're testing. It's holding it in and saying, okay, it also must, the other one, the tested one, must also converge. Because our known one is always going to be bigger than it. Have to raid and run? Absolutely. Thanks so much for sticking on in. So keep in mind, we can only do one of two things. Either we can get a larger function which converges and holds the other one in, the one that we're testing, or we have a smaller divergent function which then pushes out, prevents the testing function, or the testing series, from being able to converge. So we can only do one of those two things. If you have any other combination of stuff, inconclusive, we can't tell. You're going to have to pick something else. Alright, and since this particular one converges, then this other one that we had, natural log of I over I squared, summed when I goes from 1 to infinity, also converges. Alright. Let's see what they picked. Oh. Okay, that would have worked too. They did the integral test on this one. So actually, let's do that too. Oh, really? Huh. Huh. Okay, sure. I guess that could work. Okay, so in the book, they decided that C, they also did by ratio test. B, they also did by B, they also did by ratio test. However, no, I didn't do ratio. This was direct comparison. However, they chose a value here, a multiplier of 2, because that also works for some values out there. Must also diverge. Yeah, okay, cool. Good, I did it right. This one's ratio test tells us it converges, right? Ratio test here works just fine, right? It works because here we have this 1 over natural log of 3. It is a small value, and that works. It's less than 1, so therefore that series must converge. Alternatively, there's another way to do D. And they did it by the root test. And what they did was one of the reasons I ignored it, or I avoided it, was the limit as n goes to infinity of the nth root of n to the third over natural log 3 raised to the nth power. This is equal to L, the limit, right? So when we take our limit here, we're looking at taking the limit as n goes to infinity. This is going to be n to the third raised to the 1 over n divided by the natural log of 3 parentheses raised to the n parentheses raised to the 1 over n. Okay, and here, limit n goes to infinity. On top we get n to the, let's spread that out a bit. We got room, I mean, like, I don't know why I'm, n to the 3 over n divided by natural log of 3 raised to the n over n. So here, that exponent is 1. And now we just have a constant on the bottom. So the constant doesn't matter, we can just set that off to the side for now. And then the numerator, we need to figure out what that is. So what is the limit as x goes to infinity of the continuous function x to the 3 over x? So let's figure this out first. Here we can do a logarithmic limit. So the natural log of L, the limit, we'll make that L1, is going to be equal to the natural log of, let's do the limit of the natural log. And, nope, x. X goes to infinity of 3 over x times the natural log of x. So the natural log of L1 is equal to right, so here what we see is that we've got a 3 over an infinite value is going to be 0, and then natural log of infinity is going to be an infinite value. So we have an indeterminate form, which means that we should do a L'Hopital's rule. However, you need to have this separated out into appropriate appropriate terms. So what we should do is say, okay, this is going to be the same as the limit of the derivative with respect to x of, oh wait, hang on. Yeah, that's fine. Derivative with respect to x of the numerator portion. What's the numerator? Well, let's just make it easy. 3 natural log x divided by the derivative of the denominator portion, which is just x, right? Make it easy. So it's going to be the limit as x approaches infinity. Let's just move that down again. It's fine. All right, of the numerator now becomes 3 times the derivative of the natural log is 1 over x. So this is going to be 3 over x over the derivative of x with respect to x is 1. So now 3 over x, we take the limit as x goes to infinity. This is going to be equal to 0. So again, this is the natural log of L1. So L1 is going to be e to the 0, which is 1. Okay, so this is right here, L1. So the limit as n goes to infinity of n to the 3 over n is analog to limit x goes to infinity of x raised to the 3 over x. So here, this is telling us that we're just going to get a 1. And then we got a 1 over natural log of 3, which is, again, less than 1. Our total limit. So this converges. So exact same thing we did, but you had to go over here and make a little sidebar conversation and say, okay, we've got to take a limit of a tower function first in order to understand what's going on. So we could do the root function, it's perfectly fine. I just avoided it because I didn't want to deal with tower functions. It's fine. Like I said, we did a direct comparison, or no, we did a ratio test here. In theory, you could also do a direct comparison if you've got a good one. I don't really think there is one, but... like, just 1 over 2 to the n might be nice. Alright, E. They said, instead of doing this direct comparison, which we did, they said, do the integral test. So, we need a function, natural log I over I squared. So f of x, the analog function is going to be natural log of x over x squared. So we should go and take the integral of f of x from 1 to infinity dx. Alright, this is suggesting using integration by parts. Which, if you're in Calc 2, right, you know how to do this at this point. In integration by parts, what you're doing is you're going to take the derivative of one part and the integral of another, and then see how they compare, and try to get them to something similar that's going to make it nice and easy. So in this particular case, I would want to say that you have a u, which is going to be the natural log of x, which we will take the derivative of. So du is going to be 1 over x times dx. That's a much nicer derivative. If you tried to take the integral of it, it's not nice, right? So the integration by parts is the integral of u dv is going to be equal to uv minus the integral of v du. We can discuss how that all works, but honestly, if you know calculus at all, you already know this. This, right here, this is just a slightly different form of the product formula of derivatives. That's it. Right, this is uv is equal to integral u dv plus integral v du, and then we take the derivative of everything, dx. And in taking the derivative with respect to x, this is going to be right. So we have to slightly change it, but it's fine. Integral u dv dx dx plus integral v du dx dx. So when we bring that all together and take the derivative of this stuff, the integral part just kind of goes away. So u dv dx plus v du dx is equal to the derivative with respect to x ddx of uv. Oh, look at that. It's the product rule. So integration by parts is just using the product rule, but in integration. Okay, so then we've got dv, which we have. It's now 1 over x squared dx. And then we have to figure out, okay, what's v if that's it? So this is going to be a negative 1 over x yes. Right, because if we take the derivative of negative x to the negative first, the negative comes down from the exponent and flips the sign up front, makes it positive. And then that took down the negative 1 to become negative 2 as an exponent up top. So now 1 over x squared dx. Cool. And at this point, it's paint by numbers. So we've got this is equal to the integral from, nope, don't do that. This is equal to uv minus integral v du. So u times v is going to be the natural log of x all over x minus integral of v, negative 1 over x. Negative 1 over x times du is 1 over x dx. This is going to be rather nice. All right, uv got us that thing up front. Cool. This is, however, going to be evaluated from 1 to infinity. And since we can't really do infinity as integrals, we do have to say, okay, this is going to be the limit as b goes to infinity of negative natural log x over x evaluated from 1 to b. It's totally different. And then here, this integral is, we're going to get this positive here. Or, that's fine. This is the integral of 1 over x squared dx, which we already did that. It's dv again. So now we just need to get v out as the answer. So that's going to be a negative 1 over x evaluated from 1 to b, which is limit b goes to infinity of negative natural log of b over b minus, which means now minus a negative makes plus, natural log of 1 is 0 over 1. So that term is 0. All right, we're going to snooze that. Okay, minus the limit as b goes to infinity of parentheses 1 over b minus 1 over 1. That's just 1. As b goes to infinity, this is going to be 0. This goes to 0. And now this one is really the only question. What's going to happen with this particular thing? Well, this is going to get us a negative natural log of something going to infinity goes to infinity divided by infinity. So infinity over infinity is itself an indeterminate form. So again, just like before, we're going to take L'Hopital's rule and say take the derivative of the top and the derivative of the bottom, and the limit will always end up being the same as the original limit. So here this is going to be a negative 1 over b over 1. Alright, and then here we got a minus 1 makes that a plus 1. So here, this is going to make this limit, yeah, it's alright. B goes to infinity of negative 1 over b plus 1. So all of this stuff is going to go to 0 again, because we have an infinity in the denominator. And so our overall limit, overall limit is 1. Ah, yes, okay. We don't have the caveat where L equals 1 is a problem. So in this particular case, the, you know what, let's not even do L. Let's do the proper integral thing. Natural log of x over x squared times dx from 1 to infinity is 1 converges. So the infinite series, as I goes from 1 to infinity, of natural log I over I squared will also converge. Woo! Right. That's what our integral test said way back here. Given a series such that f is this, f of x is monotonically decreasing for all x greater than or equal to 1, as long as the integral converges, then the series converges as well. Yes. Awesome. Right. Well, I hope you all had a lovely time, however short, here. And if you have any particular questions, feel free to stop in. I do mathy type stuff on Mondays and Wednesdays. Usually math is kind of our math communication Monday. So we do like what new papers have come out in particularly math education. I am sometimes working on little math papers to check out, but I'm not particularly literate of the like very high-end mathematics. Yeah, if we choose a book at semi-random here, conformal spaces and vector and tensor analysis and Dirichlet's principle, I have some problems trying to understand that kind of stuff. So, so I don't typically work on like math research, but I'll look up math education stuff. We looked at Alex Kontorovich's treatise a couple of months ago. Sorry, just a couple of days ago, we looked at Alex Kontorovich's couple months old treatise on how to and why we should create what are called diamond open access research journals, which basically it is of no cost to the reader, and it is of no cost to the writer, so the person who actually writes the article. Excellent idea. He has some ideas for making it work, and a lot of it basically comes down to like, if you get your institution to back either you doing the research for one of these things or you doing refereeing for that journal as part of like your job, then it'll help keep costs down and sustain everything. So it's really kind of cool. Righto. I don't suspect we're actually going to see a whole lot of... Steph Woodburn just got dually, so damn. I don't think we're going to see a whole lot of people working on math tonight, but... Dr. Danny Anduza is working at paleontologizing, and tonight discussing dinosaur diet, meat and plant. So we're going to head on over there and say hi. If you would, just, speak up in chat, say hi. He's awesome, and everybody who's there is pretty awesome. So science communication, super important, and everybody loves it. I hope to see you all on Friday, where maybe we'll do another couple of runs on Against the Storm, and then we'll figure out some other times that I'm streaming. Maybe we'll do who's it's either TTRPG prep or we need to do some prep for Elite Dangerous, because I'm supposed to be leaving in 4 days, I believe, 3 days, on a expedition. So see how things go. So hope you all have a good night and a good couple of days. My name's Obi-Wan Pez. This is N Simplex Pachinko. Have a good night, everybody.